Okay. Yeah, so it was pointed out to me that I was doing things mindlessly. I wasn't thinking. And that's always dangerous, right? Always dangerous. After 20 years, sometimes I rely on autopilot. Not that I don't care about the material or I'm any less enthusiastic about it as I was 20 years ago. But, you know, mistakes. So thanks, Jack, or I should say Ginobili, for pointing it out. Which one do y'all want to do first? You want to go forward and sketch the derivative or go backwards and sketch the antiderivative? Forward. Okay. Forward. Sorry. I heard two forwards and one backwards. So let's do backwards. Let's stand up for the underprivileged, right? No, we'll go forward. Okay. F double prime. Okay. So this is the one that we're kind of practicing on because this is the one that's kind of new. So we are going to be looking at the slopes of that graph, and we're going to be plotting their slopes. So if you come over here, this slope is a really small negative number. And then as you go to the right, that slope, the tangent line, is still negative, but now the magnitude's a little bit bigger. And right there is another negative slope that has a greater magnitude. And now notice the slopes are getting really, really negative. So kind of like when we sketched the derivative of e to the x. I think we did do that back then. Your slopes go from a small magnitude negative number that approaches 0 as you go back out to the left, right? They approach horizontal, to a really large magnitude negative number that approaches infinity. So what would the graph look like? It would pretty much look like the same thing, at least over there. Okay, so I'll call that F double prime. And then we'll do the same thing over here. If you look at the slope there, that is a really steep negative number. So what is that going to be? A negative number is going to be way down here, and then that is going to be another negative number, but less in magnitude. So maybe a little higher. That could be like a -1, whatever, and then this is going to be like -0.5. And so now the slopes are approaching 0, but they're still negative. And so it turns out that the derivative ends up kind of jumping down there. And we still have the asymptote. Because the y values are approaching the x-axis and the y-axis respectively, we're going to have a horizontal asymptote on the x and y-axis. So that's the graph of F double prime. All right, so now let's go backwards. Let's see, what goes good with red and green for Christmas? White, good, let's use white. No, that's not a good color choice. Anyway, I tried. Any of these? Purple, let's do purple. Purple Christmas? No. Blue Santa. The Cops. That's a good program. Let's do that. Okay. So now we're going backwards. So we are going to use the y values now of the red graph to give us the shape. Sorry. Yeah. I don't know what's happening. Okay. We're going backwards. Blue Santa. I'm short-circuiting. Okay. So this is the one we have practice with. If you look at the interval from -infinity to 0, we have negative y values and negative slopes, right? Negative y values, negative slopes. So that should be decreasing concave down. Decreasing concave down. So it should look something like that. Decreasing concave down, and it's going to go like that. Okay? Because notice over here to the left, the y values now represent the slopes, and so that's going to be a small negative slope, so it's going to be flat. And then this y value, which is now in green because we traced over the red one, is a very big magnitude negative number, and so that's going to be a really steep graph. And I drew it there because remember that piece that I just drew, depending on the starting value, can go anywhere up or down, anywhere up or down. Okay, now on the other side, we're going to use the red values again to help us get the shape. So that is going to be positive y values, which means our function should be increasing, and the slopes are negative, so that should be concave down. So increasing concave down should look something like this. And again, we're going to be approaching the asymptotes. So that could be the graph of F. Now, of course, you can grab all of that together, and you can move all of it up and down as a unit, and it could really be anywhere. Or you can actually take any one of them and move them up and down separately, right? Their location doesn't really matter. That would just have to be given. Now, you could actually put them right on top of the other ones if you'd like, something like that. And so we can kind of go one more. Let's go one more. Let's pick brown. Let's try and sketch F triple prime. Okay? If we're sketching F triple prime, we're going to be taking the derivative of the green graph, which is still visible there. Okay? Still visible. So we are looking at the slopes then of the green one, and notice it's monotonic decreasing. And again, the slopes go from a very small magnitude negative to a very big magnitude. So that branch should pretty much trace over itself. So what you're noticing then is, at least in that branch, in that quadrant, the derivatives are going to keep tracing, not necessarily over itself, but it'll be a same shape, a similar shape. It might get steeper, less steep. But what would it be over here now in positive x land? Well, notice that the green piece that we could still see, that is increasing, yes? So its slopes are all positive. And it goes from a very steep slope here, which is close to infinitely positive, to something that is approaching a horizontal, which would be almost zero. So that would almost make it look like that again. Okay, so that's what the third derivative would look like. Guess what the fourth derivative would look like? Well, it would be the same over here in this quadrant, and then the fourth derivative would have the piece in positive x land jump back down to here. So as you keep taking derivatives, the piece on the left is going to kind of retain the same shape, and then you're going to oscillate back and forth of a piece that's going to live up there in quadrant 1 versus a piece that lives in quadrant 4. It'll jump back and forth, and it kind of gets steeper every time. All right, let's see if we can identify a possible equation for f prime, the original function. Does anyone recognize that parent function? The one that was in quadrant 1 and 3 to start with? Yeah, it looked like it could be easily 1 over x, right? Which is the same as x to the negative first. So f double prime would be negative x to the negative second, which is negative 1 over x squared. Okay, that's going to be the volcano graph. That's always negative, so that's going to be the one that's down on both sides. And it will be a little steeper. The third derivative, if you keep going, is going to be positive 2x to the negative third, which is now 2 over x cubed. And so that one is going to be back in quadrant 1 and 3. Depending on the sign of x, it's going to be positive or negative. And, of course, then it'll be steeper as well. So you can kind of confirm what's happening here. And, of course, let's go back. This is kind of getting into antiderivative. What would f be? What color? I used blue. Blue Santa, sorry. What would f be if my equation for f prime was 1 over x? What would I need to take the derivative of to get 1 over x? Natural log. There you go. The natural log. But remember, natural log, we can only take logs of positive numbers. So to increase the domain, that we can use both of them, remember what we did? We put absolute values around it. And we said that with the absolute values, when you take the derivative, you still get 1 over x. All you're doing is you're expanding your domain. Okay, and so that does look, the blue one does kind of look like the natural log of x. And, of course, we didn't have a starting value, so there could have been a what also on there? A natural log of x plus a what? Plus a 3? What would that have done? That would have moved it up 3, right? It could have been plus 33. It would have been up there. What happens to that constant when we take its derivative? It goes to 0. So maybe we could just put a big C there to represent a generic constant. Okay? So there you go. That's the introduction to anti-differentiation, or what's going to be known as integration. We go backwards, undoing the derivative. And then we always put this plus C, which accounts for a vertical shift. Okay? Sweet. All right, we got through that. I think that was a little bit of redemption. I'm still looking forward to the weekend to recover. I get a follow-up x-ray today. Hopefully it reveals everything is okie dokie. All right, let's look at example 5. AB2, 1982. What the heck does that mean? Yeah, this was actually on the AP exam. People who took AB calculus back in 1982. Whew, that wasn't me. I was a third grader. Wasn't even thinking about calculus. This was the second question. So here it is. Given that f is the function defined by that, what's up, f? Find the limit as x goes to 0. Find the zeros of the function. Write an equation for the vertical and horizontal tangent. Describe the symmetry of f. Justify algebraically. And then using the information found in APCA D, sketch the graph of f. Okay, no problem. Step 1. Well, I guess we can. Let's answer the question as we need to. Okay, the limit as x goes to 0. Never not first. How do we evaluate the limit? Plug it in. The limit as x goes to 0. That's going to be you're going to get 0 over 0. Let me go ahead and write that out there. You get 0 over 0. So remember, you want to show that the 0 over 0. Now, we talked about a couple of ways to get around that. If it's a polynomial over a polynomial, then x minus the number that you plugged in is a factor of the top and bottom. So x minus 0 or x. So we did the factor and divide out method. So that could be factor out an x, and you get x squared minus 1. All over factor out an x, and you get x squared minus 4. And then what happens with the x's? They divide out, and we can plug in. And we plug in a 0 now. We get negative 1 over negative 4, which is 1/4. And that's the answer. Now, we can pick up some extra information here, right? Let's look at the domain of f. Remember, we always want to kind of consider that first. Because the denominator is pretty much factored, what 3 values of x are not in the domain? Well, 0 for sure, right? So it's the set of all x such that x cannot equal 0. And then what are the 2 other roots of x squared minus 4? Negative 2 and 2. X cannot equal plus or minus 2. So there's 3 values. Now, additionally, we get more information just by this little piece. At 0, there had to be a what type of discontinuity? There's a hole, right? There's a hole. So, I mean, this is just us thinking, but it's good review. F has a hole at 0, comma, and then the limit value is the y value of the hole. And then the other 2, the x squared minus 4, if you factored that, x minus 2, x plus 2, it wouldn't divide out with the top. Or if you plug in a 2 or negative 2 in the top, you'd get non-zero, right? So what are those 2 discontinuities? Those must be vertical asymptotes, at x equal plus or minus 2. So that kind of comes for free just from doing that little bit of work. Okay, now, have I told you all about L'Hopital's rule? Have I mentioned it? I don't think so, because it comes up later. There is another way, and I'll introduce it to you real quickly here. There's another way to find the limit of an indeterminate form, okay? And it's due to the work of a guy named Johann Bernoulli. And so it's called L'Hopital's rule. What? That's weird. There's a story behind it. You plug in, you get 0 over 0. Okay? If you get 0 over 0 or infinity over infinity, L'Hopital's rule says you can evaluate the limit by taking the quotient of the derivatives. That is the incorrect quotient rule. What's the derivative of the top? 3x squared minus 1. What's the derivative of the bottom? 3x squared minus 4. Try evaluating that. What do you get when you plug in a 0 now? 1/4. Done. You could do it that way. Okay? That's called L'Hopital's rule. And it was discovered first by Johann Bernoulli. L'Hopital was purportedly his student and friend, but then L'Hopital kind of went out, and he gets famous because and this is kind of interesting, he published the first ever calculus textbook. You don't know what a textbook is? You probably haven't seen them in a while. But yeah, he gets credit for publishing the first calculus textbook. And in that textbook, there was a lot of calculus that was really attributed to Bernoulli, that Bernoulli had discovered himself based on Leibniz's work. The Bernoulli brothers were supporters of Leibniz, and they advanced the calculus quite a bit. But L'Hopital, as his student, kind of took his master's work and published first. And in academia, in the intellectual world, That's kind of how it works. It's not necessarily who discovers it, it's who publishes first. So for posterity, it's known as L'Hopital's rule, but every time I say that, I think Johann Bernoulli. So anyway, we're gonna do that a lot more later in the year. There's a whole section on that because we're going to look at other indeterminate forms. So that's a legitimate move. If you want to do that now, you're welcome to do that. It kind of replaces all of the RATCON and LCM over LCM method, right? So why didn't I teach you all that back in that section 1.4? Why did I just show you this derivative trick now to evaluate a limit? Well, yeah, true. You don't see the whole or VAs. You don't factor it out. You can't analyze the domain. I'm showing you now another way to show you that it works, or we learned the way that you could do it algebraically, and then we can confirm that it works. The real reason is, remember, back then, we didn't even know what a derivative was, right? Remember that? We were coming up with the idea of a limit so that we could pour the foundation for the house of calculus, and then the idea of the limit helped us come up with the definition of the derivative. So we used the limit to help us derive the derivative. We didn't know what the derivative was, so we couldn't have used it. But now that we know what the derivative is, it turns out that you scratch my back, I'll scratch yours. The derivative can be used now going backwards to help us evaluate a limit. So anyway, that'll come up again later in the year. You could have done it either way back in 1982 and gotten full credit, as long as you had the right notation. All right, find the zeros of a function. This is good review. How do you find zeros of a function? What's another name for zero of a function? Yeah, x-intercepts. Roots is the old-timey word. That's one I learned. They're the solutions to f of x equals 0. Okay, they all mean the same thing. So let's take this version here. I'll just copy that one. Okay, and I'll come over here and let's paste it. And I'll put f of x in front of it. And then I want to show that I'm setting it equal to 0. Okay? But now, when is a quotient equal to 0? When the numerator is 0. Now, bless you, if you haven't divided out the x yet, and you just set the numerator equal to 0, that would be fine. That is the original numerator. But then if you solve that, you get x equals 0, and then you get x equal plus or minus 1. Are all three of those zeros or roots? Are those x-intercepts, all three of them? No, x equals 0 can't be a 0, a root, because it's a whole. We already established that. And so that's kind of why they had you do part A before they did part B. They're trying to help you out. So really what you could do, if you ever have a whole, you can actually get rid of that, identify it, but then for the rest of the problem, you can use what's left to do all the rest of your analysis. Because the only difference between the one in green and with the x over x there is that it has a whole, which we've already accounted for, okay? So just set the numerator that has what's left equal to 0. Okay, so x equals plus or minus 1. That's it. You don't have to write it as ordered pairs, but you could. 1, 0, negative 1, 0. All right, write an equation for each vertical and horizontal asymptote. Okay, so we've already kind of done that. Wow. So we have a vertical asymptote at x equals negative 2 and 2. It said for each, so I would list them separately. X equals negative 2 and x equals positive 2. And you're not going to have to justify that, okay? We kind of did that work over here already. But how do we find horizontal asymptotes? That's the end behavior, right? So that would be the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. Now, you probably didn't have to show that because it doesn't say show your analysis or show the work that leads to your answer. But just to remind you, this is how we find horizontal asymptotes. So coming back over here, the expanded version is the best version. Again, once you get rid of the whole, you can use what's left. So you look at the leading term over the leading term. They're growing at the exact same rate. So remember, what is the limit? 1, leading coefficient over leading coefficient. And it's the same on both sides. So both of those are going to be 1. And so you could just say, so f has a horizontal asymptote at y equals 1. But if all you wrote was VA at these two guys and HA at 1, that would have been enough. Okay? All right. Describe the symmetry of the graph and justify algebraically. So we did this in pre-cal, right? Remember, The test is you replace x with negative x, and all you have to do is show that it equals the same as a positive x, right? Negative inputs and positive inputs give you the same thing. So let's go ahead and do that. Again, you can use what's left, x squared minus 1 over x squared minus 4. X squared minus 1 over x squared minus 4. So if you plug in a negative x, it's going to look like this. Parentheses negative, parentheses negative. You're going to have to show that you're substituting it in. That's what they're going to see. That's going to earn a check right there, showing that you're substituting in a negative for an x. And then you simplify, and of course, negative x quantity squared is positive x squared. Same thing in the bottom. And then you just say, oh, that's equal to f of x. So f is even, or describe the symmetry. So f is even and has, I would probably throw that in there, and has y-axis symmetry. Do you have to say both of those? Even and has y-axis symmetry? Maybe not. If you were only to say which one of those, which one based on the specific question would you say? Yeah, I would say y-axis symmetry and not say even than the other way around. Yeah, because it specifically used that word. Okay, so far it hasn't really been too bad. I mean, it's been review for us, but we haven't broken a sweat or anything. So now it says sketch the graph. Okay, we got it. Sketch the graph. Let's see what we can put together so far without having to bust out any more calculus. If you have asymptotes, you always want to sketch those first because they act as guidelines for the function. So we had one at -2, so let's just call that -2, symmetrically +2. And we had a horizontal asymptote at 1. So there's 1. And then we'll do that like that. Okay, that looks good. Dotted line instead of dashed line. We know it has symmetry, so if we can get it in, quadrants 1 and 4, we can reflect it across. What else do we know? Oh, there is a hole. Where? Don't forget the hole. Okay. Okay. I'm going to have to come back to this one. Okay? Good thing. We'll keep this in mind. Good thing. They're having us sketch it. Let's go ahead and plot the hole. Where do we say there was a hole? At 0, 1/4. At 0, 1/4. That's going to be right here. 0, 1/4. Can it still be an even function with a hole at 0, 1/4? Yeah. You'd have to be careful, though, because if it were over here like at 1, 1/4, then we would have to have another one at -1, 1/4 in order to still have symmetry. So what I said over here about testing for symmetry, you actually don't want to do it with the x out of there, because then you can miss it. So you would want to show it right here. So let's just kind of redo that again. I apologize for that. But it turns out that it's on the y-axis. So it will still end up being even. So you get -x cubed minus -x all over -x cubed minus 4 over -x. And that's probably where you get the check. And now if you simplify, that's a -x cubed, and that becomes +x. And then this becomes a -x cubed and a plus 4x. So notice all the signs changed, didn't they? And so what you could do is you could factor out a negative from the top, and then you could factor out a negative from the bottom. And now what happens to the negative over negative? They divide out, right? And so now those divide out, becomes plus, and that equals f of x. So I haven't seen them do that in a long time, test for symmetry. But, yeah, make sure you test for symmetry on the original one. Because if you had one hole and it wasn't perfectly on the y-axis, that's enough to damage the perfect symmetry. So we would have gotten lucky on our graph, but if I didn't come back and redo this, I would have missed that. Okay. What else? What else can we do? What are we doing? Oh, we're almost out of time. Okay. X-intercepts, right? Where were they? 1 and -1. So it's going to be here and here. So that's enough. It's going to look like this. It's going to pass through there. hit that point. Because of the symmetry, it's going to hit that and go down. All right, now on the other sides, let's put arrows there. On the other sides, it cannot live down here. Why not? If it did, what would we have already found? Another x-intercept. So you could either plug in like a 3 or a 4 and see if it's above 1 to determine where it lives. But you can also say because there's no other x-intercepts, it has to live above. And so right there, that would get you full credit. Let's label it as F. And there's a pretty picture of the graph. Okay, and that hole, I would probably make it a little bit bigger, but there you go. All right, have a spectacular weekend, and practice, practice, practice. Let's quiz on no, not Monday. We didn't finish. Let's not quiz on Monday. Let's finish on Monday, and we'll quiz on Tuesday.